Good morning, everyone. Welcome to our final event for the iFishIENCi project, this European Horizon 2020 Research and Innovation Action. I am Dorothy Duncan, and I work at the University of Bergen as a researcher in responsible research and innovation. I'd like to invite on stage the project coordinator, our colleague Tomasz Bartosz from the Aquaculture group in Marfa. So please, Tomas, tell us a little bit more and give us an overview of the Research and Innovation Action.
Thank you, Dorothy. Maybe I can start with. So thank you, Dorothy, and welcome everyone on our final meeting. So the iFishIENCi study started with a long time ago, more than 5 years ago, when we decided with Dominic and with the team that we join our forces and submit a proposal together for the European Union Horizon 2020 program. And we developed the consortium where our aim was to represent the industry, the companies, the science, and also the NGO sector of the aquaculture. So the consortium has helped. We still help because we still have 1 month from the project. We have 16 partners in the consortium. From these are SMEs. We have 4 research institutes, 2 universities, and we have the NC Seafood, which is representing the NGO sector, the aquaculture in the project as a cluster. And in terms of the countries and aquaculture production areas, we cover the whole Europe, I see. We cover the main species of the aquaculture in Europe, like the Atlantic salmon, sea bass, sea bream, and the freshwater aquaculture, like trout and African catfish. But we also work with species which are important for the world aquaculture to feed the world, and which plays an important role in the aquaculture development of the bird, like the tilapia and Asian sea bass, for example, which are emerging new species. Because the concept of the project was not just develop something for the European aquaculture, but develop the potential of the European aquaculture to export technologies for the whole world. As usual, in the Horizon 2020 goals, the project aimed to solve all the problems of the aquaculture, including one project. So we go a little bit with everything. But our main focus in the iFishIENCi project, we can say that it was the waste from aquaculture regarding the environmental emissions. One of our key areas area was the feed sustainability, efficiency of the feeding, and alternative feeding readiness. But we also that we can mitigate the climate change impact, and also we have some results in terms of the more economic production methods and the social acceptance of the aquaculture. The structure of the project was arranged around 5 main pillars, which are in the orange box. And the logic was that we wanted to work with the new technologies. As Bridget mentioned in the introduction, we wanted to introduce the aquaculture 4.0 technologies in the existing technology, and at the same time work with the feed development, feeding system development, but do this on a way that can support the sustainability and the responsible research initiative and innovation in the project. And so in the project, which today more than and we hope that this works provide nice area for the project using. So thank you for your attention, and I wish you a nice and useful day in the whole consortium, and I hope you will enjoy and it will be useful for your presentations about our project.
Thank you so much. And we're going to hear from you, Essa, later when we get back to the Hungarian story. I'd like to introduce my colleague Inma Sanchez from Lertat in Barcelona. Circularity is really important for sustainable aquaculture, and Inma has been working exactly on this topic. So, please, Inma.
Just to give you an introduction on the topic of circularity or circular economy, most of you already know about this, but basically the circular economy is a model of production where we should reduce waste and we should extend the life cycle of the product. But we think about aquaculture. I would like to give some feedback from you at the before I start the presentation. So just take a picture or scan the code, let's say, and provide a few words about how do you think that the circular economy is embedded or is connected to aquaculture. Yes. People from home, I think that they could also provide feedback. Yes, 30 seconds. Okay. Regulation, good business, smart, sludge. Okay. Do we have more feedback? Okay, otherwise we can go back to the presentation. Actually, we made the same question 2 years ago, and I can see something that is in common, that is probably the sustainability. So the sustainability is very connected to the circularity, and it's good to think to work on how the circular aquaculture should be sustainable. Probably we have to make some effort to ensure that the circular aquaculture is sustainable enough. With the circularity, well, we can see the circularity in the technical cycle is more or less easy to follow. A material that can be manufactured, can be used, can be after the end of life, it can be collected, and then can be used again, or can be treated in a recycling system or in a reuse system. But if we look into the biological cycle, sometimes the cascades are not the same. So we can use again and again a biological fuel, but in the end, the extraction of biological feedstocks would be restorative as well. So we have a big difference, let's say, between biological and the chemical materials. And aquaculture is actually in the biological. If we look into the aquaculture system, just some very basic approximation, we can see that the feed sometimes fully used. We hope so, but the thing is that some of the feed is lost. And on the end, we have waste. But what about if we talk about nutrients instead of waste? So the circular aquaculture should tackle the nutrients that are used and the nutrients that are lost. So probably we should change the paradigm and not talk about waste, but talk about nutrients. In the traditional system, like the IOTA in Asia, for instance, we can see circular outputs where some of the species and uneaten feed is taken by extracted species. This is not new in other countries that we are promoting more and more the IOTA as a circular production system in Europe. If we look at the RAS system, it seems like circular in the sense that some of the waste are circulated by drum filter, some biofilter, and then it can be used again in tanks. So maybe it's circular in the sense that we can concentrate the streams from aquaculture and also they can create value and create business opportunity to use that more efficiently. We have also another example of circular aquaculture that is the pond system, where the nutrients runoff water can be used in crop production as irrigating water. Also, the runoff from the system can be used. So, the principles of circular economy are perhaps already embedded in traditional aquaculture system, but there is a strong need to provide of aquaculture technologies, and also the need for increasing up in predominant production system. So in this context, we started to work with efficiency project, and we started to create a circular solution at level. I mean, reuse, recycle, recovery waste, let's say, nutrient. And so at the relevant scale, in the sense that aquaculture is coordinated with other sectors to provide synergies, and at the global scale, providing products that can improve sustainable or ensure the sustainability of aquaculture. And the circularity is, in fact, a key aspect of the project, in the sense that we are moving from a linear process to a circular. The basic idea of circularity in efficiency is that algae and yeast can be cultivated with waste streams from fish farm. These algae and yeast can be formulated into new feeds or can be used in other value chains. And then we show that circularity should be measurable, should be a measurable attribute, and we started to think how what to measure and how to measure the circularity. And then we saw that we should measure how well the things that we were doing in the new value chains perform the concept of the circular economy. We also agreed that we had to measure materials flows of the restorative aquaculture system, and then we started to see how we could quantify the inputs coming from virgin materials, the materials that transit and components that are connected. And then we should measure the efficiency of the recycling processes to use cycle. So if we look into the process, the SIG process developing efficiency period, we identify different waste times and then opportunities for valorizing this waste stream, not only for waste, but also for water. This is particularly relevant for the RAS system, where we can collect sludge. And then we identify key parameters we monitor to measure circularity. One of them is the of raw material input flow that we can have in the feed formula, the portion of restorative materials that came from reused or recycled sources, and finally, one key aspect is the utility of the feed that is that has a circular formula. If we don't have a good utility of the feed, then we don't have circular principles in the process. So the challenge was how to provide evidence metrics, and we saw that we had to develop a framework for assessing the circularity of aquaculture. And then we started to elaborate on some key indicators that, in the end, they led us to develop and to demonstrate with figures that when we have nitrogen assimilation, we have higher nitrogen assimilation, we have higher circularity. But we should demonstrate with figures through the key indicators. And then we have been contributing for these 5 years. We have contributed to the circular aquaculture, providing a first approach to a common definition for the sector. We have identified and characterized circular feed formulas. We have studied more efficient feeding systems. We have developed circularity application framework for innovative allocation routes. And in the end, we have provided an evidence-based metrics for assessing circularity. We have been focusing on 4 main indicators to evaluate the linearity of the feed, the nutrients recovery, the material circularity, and the zero waste attributes. And we wanted to go further. 3 years ago, we saw that there is nothing on the sector related to a common approach for circularity definition, and we started to work together with other people from other projects. It was a big collaboration between many people across Europe and other people from Europe. And we elaborated on a policy recommendation document providing some ideas to start with definition, some ideas and recommendation to evaluate the circularity and some strategies to tackle the regulation challenges. So if you want to know more about these indicators, we are having our waste to value workshop tomorrow, moderated by my colleague Monse. So you are more than welcome to participate tomorrow and be aware of this. Thank you.
Thanks a lot, Inma. So yes. Again, tomorrow we'll be in this same time, same place here in the morning for that waste to value workshop. One of the biggest innovations in iFishIENCi is something we call iBoss. So I have my colleague Franck Le Gall from EGM in France to tell us a little bit more about that.
Hello, thank you. Good morning, I'm Franck Le Gall from EGM, and I'm going to introduce the iBoss, which is, let's say, the IT platform being used in the iFishIENCi project, or developed in the iFishIENCi project. Maybe to start, when we want to deploy such a platform, first question is, okay, what is the need? What do we want to answer to? And we had a number of discussions with stakeholders in the project and outside of the project to identify the different needs. Let's say nothing really new, but always good to state them down again. That, okay, we need to reduce the inputs in terms of food, in terms of energy. We want to reduce waste, because waste is waste. In more or less what we can do with waste, but if we can reduce them from the beginning, that's always better. Obviously, we want to increase fish production in quantity and in quality. Both aspects are quite important. And for that, we need to improve the process planning and all system maintenance, stock availability, and looking at the whole value chain in the sector. And overall, and of course, in total, looking also at the reduction in environmental footprint. How we do that is using data. So we need data, and from data, we will be able to build rules and help informed decision through some rules and recommendations. Data, there are a lot of data. Quite often we think about sensor data, IoT data, which is providing information about water quality, the equipment and so on, but it's not only this. It's also feedback from the farmer, so it can be from farms and so on. So it's really a lot of different data. It's also data from the suppliers, which is providing the food with all information on the food sticker and so on. So this has to be collected from a number of different ways, from the sensors, from forms, from online interfaces, and so on. And once we get all this data, then we can start building on rules. And it's not only about artificial intelligence, machine learning, but it's also about capturing the expert knowledge from the field. So we have to allow these two interactions in the platform. And a number of different algorithms can then, once this is achieved, be developed, and the next presentation will tell us a bit more on that. So how we did tackle that in the project? If we want to develop an IT system, so as I said, we have a number of solution providers for sensors, for the systems, for the hardware, for the software, and so on. What is my best approach for that as a farmer? First is, okay, I will look independently to each different vendors which is selling me the perfect solution, and I will install all of them in my farm. Okay, everything will work fine, but then, okay, everything will be in silos. So I won't be able to easily exchange information from one solution to the other. So next, I could go to a big vendor saying, okay, I can do both and I will integrate the whole thing. That's perfect because then I will have the whole solution working together, all functions being interacting. But then again, one issue is lock-in because I'm only with that vendor. So what if I want to go to another vendor that may be a competitor that will not go, would not like to cooperate on that. So the approach we took in the project was working on interoperability, saying that we have different solutions from different vendors. We can say this one is better than this one. It really depends on the case. But what is important is that each solution will be able to interact with one another through interoperable interfaces. And this allows making an ecosystem. So this is technically, I won't go too much into the technical details, but basically we have a cloud which can be in the cloud but can be on-premise depending on where you want to put your data. We will have data producers, as I said, sensors, but not only, that will provide data. We'll have data consumers that will make use of that data. It can be the farmer looking at dashboard, but it can be also a feeder, a pump, and so on, which is being controlled by some data coming down. And obviously, we'll have data processors. So things which will get data, run some algorithm, provide feedback. Oh, that's a good time to feed. Oh, stop feeding now, and so on and so on. We didn't want to reinvent the wheel. So what we went to ETSI, which is one of the 3 official European Standardization Institute. We took one of their specification, which has the ugly name of NGSA LD, but which is meant to really allow exchange of information across different domains. Because aquaculture is aquaculture, but it's using information from the water domain, from the energy domain, from the transport domain, and so on and so on. So we need to exchange data across these different domains. So, idea and what we wanted to push, and I hope this afternoon we'll have the opportunity to discuss this further in the workshop where we'll have roundtables, is, okay, we provide a solution which is multi-vendor, so no vendor locking, it's quite open, extensible across the value chain. In the project, obviously we can't answer everything, so we had to focus on a particular aspect, but this can be extended across the value chain. With innovation capabilities, if you want to add new modules, new emerging topics, you can, because there are these interoperable interfaces. And this afternoon, we'll be pleased to present you a bit more into or to enter a bit more in the detail of what we did. Thanks a lot.
Thank you. Thank you, Frank. So Frank just gave us an overview of the infrastructure and the ins and outs of iBoss. But now we're going to show you iBoss in action. And this is one of the really cool demos that we've been doing in Greece with our colleagues Dimitra and Nikos from the Hellenic Marine Research Center in Crete. So you guys are going to show us how this has all worked in practice.
Yeah. Hello. Good morning, everybody. Following what Tamas introduced as the general objective of the project and what Frank presented as part of the iBoss platform, I'm going to present you together with Dimitra, with my colleague Dimitra, the work we did in Greece towards an intelligent feeding system to control the feeding in marine cages. I'm going to start a little bit with what Frank said. Our target was from the beginning to provide a decision support system in order to reduce cost, to reduce waste and environmental footprint, and to improve process planning, stock systems, and etc. Exactly similar graph as Frank, we need data and we expect to provide tools. But the general idea that we wanted to provide tools using principles of what it is called recently precision farming. And this is more or less what it is also said aquaculture 4 approach. Always when we want to work with fish, we have to consider some parameters, some things that we have to respect. And this is the species-specific requirements of the fish and also the species-specific behaviors of the fish. Of course, we need to understand first the behaviors in order to respect them. And we have obviously need to respect the welfare of the fish. And for this, we need appropriate methods to monitor the behavior and to determine the fish requirements and to link with any possible husbandry activities. In other words, we need to find a way to allow fish to talk to us. And speaking about feeding, the main question is how we can feed smart. And we know that feeding has different drivers: the environmental conditions, the developmental phase of the individuals, the fish status, and the metabolic state of the fish. We have several tools to monitor the environmental parameters. We have methods to estimate the growth and that's the development. We have models to predict the metabolic state. And we have behavioral observations until now to, to give us an indication of how fish are and the general condition. And the main question in this project was how we can use this feeding behavior to achieve a more intelligent feeding strategy. In other words, the questions to answer was, can we optimize feeding by understanding when the fish are satiated or close to satiation, or when the fish are hungry? And can we correlate the swimming activity of the fish to define this satiation or hunger levels? When we feed fish, particularly in the Mediterranean, we have some observations. And you can see here in this video what I'm seeing. It's obvious that the fish present a high density. They start having a circular motion. They have an increased activity, most probably related to higher speed. And we also observe that the fish approach the surface during feeding. So what are the potential indicators that we can measure out of these behavioral indicators? We can measure the distribution in length. We can measure the cohesion of the group, the change in speed, and the directionality polarization. These are the technologies that were available, or we wanted to use, better to say, in the frame of iFishIENCi. iBoss has been described before by Frank, and FishTalk to me is a technology that allows us to have a continuous data collection from the fish. Fish behavior, in this case, that I'm presenting here, and to integrate with other technologies in order to have a system of continuous observation that allows us to have a continuous picture of what is going on in the farm. So I'm going to show you a little bit how we implement this FishTalk to me in our case in the Mediterranean. We use environmental sensors, obviously, and then we have a combination of tools for monitoring feeding behavior, like cameras, echo sounders, telemetry tags, and so on. And we want to investigate different characteristics of swimming behavior and its variations in relation to feeding. We wanted to select appropriate parameters to serve as decision indicators, and wanted to quantify thresholds to decide on these parameters and to transfer all these values to the iBoss. Schematically, it's what it's showed here: the fish, the different parameters that we collect, and then the iBoss cloud and the decision support there. Where we did all this work, at HCMR, we have a pilot farm in Greece, in Crete, in the Bay of Souda. We have a farm close to a commercial port, and this is how the farm looks like. We have been using a circular cage of 40 meters in perimeter, and 9 meters depth. I know that this is not a commercial cage, but it is as close as possible to the commercial. It's a pilot scale application, and we ran 2 or 3 production cycles using European sea bass as species of interest and species to work with. We use all this period in order to develop first applications that allow us to observe what is going on, and then to collect also the required information that were required for us to work. What are the tools that we have been using? Environmental sensors for live streaming, submerged cameras, echo sounders, and then telemetry equipment. This is the schematic representation of the setup that we had with the environmental sensors in different depths, the camera, the echo sounder, the feeder, and then everything with wireless transmission to the iBoss. It's an easy setup, straightforward installation, no real operational problems, apart from some network failures, which mostly related to the bad weather conditions, which is something that we anticipated and we could tolerate. And I'm coming actually to what are the data that have been collected. And I'm going to start with environmental monitoring. 2 partners, Oxyguard and Bioceanor, provided us with sensors, and we had an online data collection, as you can see here. And all this data were transferred to the iBoss that our colleagues from EGM has implemented. So we had solved somehow the environment part of the problem. And then I'm gonna start presenting some of the results we have about the behavioral monitoring. As I said, we ran several trials in order to achieve this. Obviously, we are not going to present you all the information and all the data that we have collected, but we have selected some of this data to present with Dimitra. I'm going to start with the acoustic telemetry. Acoustic telemetry, for everybody knows that, we have some tags that are implanted on the fish, and then we can monitor individual behavior of the fish in the cages. We have done this implantation, and we have studied the effect of the implantation on the behavior of the fish, so that we are sure when we transfer the fish in the cage that we observe the actual behavior of the fish and not the effect of the tagging. And then we study how the fish behave. And we came up with two interesting results. The first result is what we call food anticipatory activity. And you can see here in blue that after sunrise, you have the fish react to the environmental change by increasing their activity, anticipating for food. And this is something that we knew from the biology of the species. It's a species-specific characteristics of the sea bass, that it has this behavior that they are foraging in the morning and also in the afternoon. So we have seen this food anticipatory activity, but also we have seen a food anticipatory positioning, as you can see in these two graphs. And you see here a concentration of the fish and 2 times sludge in the morning and just before the sunset. That is again correlated with the intrinsic characteristics of the species. These results gave us the first topic of the first idea of how the sea bass is behaving. It has been in collaboration with NORS, with our colleagues in NORS. And last week, the paper came out with this information. Now, Dimitra is going to continue with some more interesting results on the feeding behavior.
Hello. To understand how the fish change their behavior around feeding times, we designed a series, a long-term experiment, where we changed different parameters, feeding parameters. These were the feeding frequency, the feeding time, and the feeding quantity. And we analyzed all this data by using a model that we had developed, a system we had developed previously that helps us to track the fish. The first behavior parameter we tested was the speed of the group, and here you can see how the speed changes in time for different feeding quantities, the normal, reduced, when there is overfeeding, and when there is no feeding. On the vertical line, we see when feeding starts, and the green bar shows us, down here, shows us the duration of the feeding. What we can see from this graph, we can extract three things. First, we can see that we can define a possible speed threshold over which there is an increased activity related to feeding, and this is shown here in the horizontal line in the middle. The other thing we can see is that there is a difference in the duration of the activity, of the increased activity, for the different feeding schedules. And the last thing we see is that there is difference in the symmetry of the behavior. What I mean with this is that if you look in this plot, we see that the speed gradually increases just before feeding and gradually decreases immediately after feeding. Showing that there is a symmetry in the behavior around the feeding time, when the feeding starts. This is not the case for the reduced and the overfeeding scenario, where we see an asymmetry around the feeding time in both cases, but in a different direction. So we wanted to quantify this asymmetry. We found a way to quantify this asymmetry, and this is what we show you in this graph. The y-axis shows the asymmetry that is taking place for the different feeding scenarios. The different lines are the different feeding scenarios, and I want that you focus on the blue line, which is the asymmetry seen when we have normal feeding. This line is horizontal and it's close to zero, suggesting that there is an asymmetry around the feeding time. As we saw also, there is a symmetry, around the feeding time, and it's what we saw in the plot before. In contrary, you see that the green line and the yellow lines, that are the overfeeding and the reduced feeding respectively, they show an increase and decrease in this asymmetry, suggesting that there is asymmetry that is not that does not have the same direction. And for the fasting period, we see that there is no specific pattern of activity. Of asymmetry. So this result is very nice for us because we can quantify this asymmetry we see, and we can use this as reference lines in order to control feeding later. So this graph next shows the duration of the increased activity for the different feeding scenarios. The lower the value shows that there is a shorter period of increased activity, and we can see that when we have overfeeding, the duration of the increased activity is much shorter than we have normal or reduced feeding. Here, the other behavior parameter we tested was the feeding behavior index. This is a parameter that shows how densely packed or crowded are the fish during feeding. You can see that this parameter is very high when feeding starts, and as the feeding progresses, it decreases, suggesting that there is a relaxation of this crowding. So we have the similar plot with the first one, but now with the feeding behavior index. And what I want to show here is that the fish, when feeding start, react. They go very densely, in high densities around the feeding and the feed. And here we can see this by this step. And there are differences between the different feeding scenarios. When we feed with reduced quantities, we see that the fish react massively and they have a stronger reaction, which is depicted in this strong step and big jump. And this is not the case when we have normal feeding or overfeeding. And of course, obviously, when we don't have feeding at all, there is no apparent step seen as expected. The other thing we did is that we automatically grouped the feeding behavior index into 4 clusters of behavior, as you can see here. If you focus on this plot here, you will see that we have, for the normal behavior, we have one black cluster that shows the pre-feeding behavior. The red and the gray cluster show the behavior during the feeding, and the blue cluster shows the post-feeding behavior. The interesting thing is that we applied this clustering also for the other feeding scenarios, and what we saw is that there is differences in the clustering. Here, during the overfeeding scenario, you will see that this blue cluster, that is the post-feeding behavior cluster, appears before the feeding starts, before the feeding ends, indicating that possibly there is still, the fish are much earlier satiated. The opposite happens when we have reduced feeding, where we see that there are the two feeding clusters, the feeding clusters are apparent even after feeding stops. For the no feeding scenario, we see that the black cluster remains even at times that we know that the fish expect to feed, to get some food, but they don't. So also this clustering could be a possible tool for us to use to understand how the feeding was in a day and to control the feeding the following days. We also run a change point analysis. It's a well-known methodology for automatically detecting when feeding starts and when feeding ends in a signal of the feeding behavior index. The automatic detection of the feeding behavior index of the start enabled us to develop a model that can make predictions of the feeding behavior index in future seconds, in future time. So what we see here is we built a neural network and we trained it, and then we tested it in the 3 different feeding scenarios. And you see here with blue line the actual values of the feeding index, and with orange line is the predictions we made after a few seconds. So as you can see here, these 2 lines are very close, suggesting that we have a very good tool for making predictions on how this feeding behavior index is going to change in the following seconds. And this is a very nice result because it gives us the opportunity to have a real-time control when the feeding is taking place, in fact. Yeah.
And I'm going to continue making a note that the data that Dimitra showed are, for the first time, a time series of the actual behavior of fish in the cage provided with numbers. Because until now we have an overview of what is going on with the fish in the cage, but we never have real numbers that giving us the opportunity to study and make analysis, as Dimitra showed before. So can we use all this information towards control feeding at 2 levels? One, at real time, as Dimitra mentioned before with this model, or by using an approach of evaluating what has happened today and adjusting and apply tomorrow. Yeah, we are really close to this, and I would say that with environmental parameters we are already there because we have applied. We have set some thresholds in relation to the dissolved oxygen and to the temperature, and we define when we can continue feeding or cease feeding depending on the environment. These are obviously parameters that are user controlled, and for the case of the sea bass, we said that 50% saturation of oxygen is for us a cutting edge point to stop feeding, or the thermal variance between 12 and 28 degrees. So this is something that is already applicable, and it's a straightforward approach. The next and most important thing is the behavioral thresholds. We have shown you several parameters that we have studied, particularly the fish speed, and Dimitra showed the symmetry of the motion, some threshold values, and the duration of the excitation that can be used potentially as control variables for the feeding. And we have also this new feeding index and the clustering comparison that we have shown, and the predictive model that has been developed that will allow us to control the feeding. We are not there yet in this, but we think that we are very close to be there. And the constraints for this type of work is the long-term trials that are required and the large data set. Actually, we are still running the final experiment in this project, and we hope that we are going to have the opportunity to get some better results on this. So if I want to summarize a little bit what we have achieved, we have developed a methodology to detect and monitoring European sea bass in cages, and we have applied also this methodology for the Atlantic salmon. It has been tested positively. We have a method for automatic detection of feeding events, and we have developed the feeding index behavioral parameter that give us significant information on the behavior of the fish during feeding and around feeding, and also together with the speed of the fish, give us a first estimation of satiation levels and thresholds that can be used. And most important is that for the first time we have integrated the fish behavior and environmental parameters in one platform, and we have an unprecedented interpretation of fish status and prediction for their needs. And also we have achieved defragmentation and digitization in a single system. And to our knowledge, this is the first time that something like this takes place. I would like to thank all the colleagues that participated in this nice exercise during the course of the project. BioCeanor, EGM, Oxyguard, Norse, and of course my colleagues at the Hellenic Center for Marine Research. And obviously we are ready to answer questions if there are. Thank you.
Thank you so much, Nikos and Dimitras. So we do have 5 minutes for questions from the audience. I have one question that I have myself, and also for our colleagues and network that are following us on the live stream, we have a chat. So please feel free to put in any comments or questions that you have there. I think it is very impressive to see how all of the quantification of behavior now can be tracked, recorded, up to the cloud, and decision making. But the question is, how species specific is IBOS? So you've been using European sea bass here. Is IBOS plug and play for any species that we can have in the world, or how does it work if I want to use this for my species that I have at my farm?
The part for the environmental parameters, the monitoring of the environmental parameters, I think it's straightforward. It can be applicable anywhere, everywhere. IBOS is a generic platform, and to measure oxygen and temperature and pH and all this stuff is the same everywhere. Mm-hmm. But if we come to the biological and the behavioral parameters, then we have to be actually very careful, because each species reacts in a different way. Right. And it has its specificities. And maybe the parameters that Dimitra has shown before, the feeding index, the speed and all this, give us an indication of how the fish may behave, but certainly we have to do specific studies, and species-specific studies.
Bringing in the biology.
Yeah, exactly.
Right.
This at least for me, is for sure. We cannot apply directly the findings of the sea bass in salmon, right, for example, not even in the sea bream.
Right. So environmental stuff, that's plug and play. Yeah. That's easy. But the actual behavior of the species, that's where we need the biology and that species know-how. Good. Yeah, there was a question. How far into the day can the algorithm predict feeding behaviors?
We have tested it right now for, let's say, a few seconds.
A few seconds.
We can go up to some minutes, but we need to train more the system in order to be able to achieve let's say, longer predictions. Yeah, or
but to tell the truth, if we are going to be extremely happy if we have stable and coherent results for half minute.
Yeah.
Because this is already sufficient to control, to say stop or continue. Because this is what you need actually.
Yeah.
And if you go half minute in advance, then this is going to give you a huge advantage in hand.
Great. Any questions here from the audience? Thumbs up. Everybody thinks that this is a good innovation that can be helpful for aquaculture, not just in Europe, but also perhaps around the world.
There came a question on chat right when you...
Great. Our question is, what percentage of the fish captured on camera is considered sufficient to gain genuine insight?
If I understand correct the question, the colleague is speaking about catching feed. That means we don't monitor the feed.
So
loss.
Which percentage of the fish captured on camera is considered?
Of fish.
Probably when you have to put in the telemetry tags. The cameras, yeah.
We didn't mention this. We use cameras. Mm-hmm. So we can detect, depends on what you want to look for. If you want to look for the feeding behavior index, you don't go to the individual fish, but to the whole group behavior. Mm-hmm. So the cameras are located in a way so you can see, you can have a very good view of the density of the population around the feeding, so right, that can help you to estimate how this feeding behavior index changes over time. So you don't really need a specific number of fish, but you need to have a very good view around the feeding place, and this is enough. For the speed, we cannot obviously track all the fish because it's a quite densely packed population, and our algorithms detect, let's say, 30 fish maximum per frame, let's say, for a few seconds. But that's the best we have done so far, and we can see that the speed is highly correlated with what we also observe, what the changes we see. So we think it's quite a good representation, but we definitely always improve the system to get more and more fish.
And just to add on this, on what Dimitra said before, we know that there is a problem if we have a huge cage and we have different feeding locations, and not only one feeder, but a different feeding location. And then we just need to have multiple cameras to see how the fish behave, depending on the distribution and the feed that it is delivered and how they react in this delivery of it.
There's one more question before we move on, and that's for the behavioral events you analyzed. Did you study if there was a conditioning from pre-study management?
Yeah, we took care about this, and that's why we have not considered periods of underfed or overfed individuals more than 4 or 5 days in order to be sure that there is no the fish are not accustomed to the new situation, and we repeat this trial after let's say 2 or 3 weeks of normal feeding, so that we are sure that fish are coming back to the standard classical behavior that they have before we expose them in differences that we have seen.
So you mentioned in your last slide that this has been a big team effort with the different collaborators that we've had. And after lunch today, we're going to have the iBus workshop where some of our other partners from BioOcean Nord, for example, are going to go more into the details about the different integration aspects of cameras, sensors, cloud infrastructure. So I think
that one more question came, but I have to make one comment. And
yes,
it was indeed a nice collaboration between all the partners that I have shown there. And I haven't mentioned because we didn't have the time, but maybe I have now a few seconds to mention it. We have a very good collaboration with BioOcean Nord, analyzing for the first time both behavioral and environmental data. And we came up with something that it was, for the biology point of view, was very significant. Because apparently, just correlating the two data, we came up with a value for the critical temperature that seabass seems to have as an optimum. And this coincides with what we know from biology from years now, that it's about 24, 25 degrees. But this came just from the analysis of the behavior, of the motion behavior of the individuals and the environmental parameters, which for us is significant that this is another issue that we have to explore further in the next project, most probably, or in collaboration with the companies, but certainly give us the opportunity to have a step forward. And obviously, this is something that cannot be done by one organization. It requires teamwork, and we are very happy to have to be a part of this nice consortium with all these good partners.
The collaborative aspect, very essential. One more question, because there's a question on the cost of these technologies, cost of iBus in developing countries. What are maybe the bottlenecks there in developing countries?
I don't think that we are ready now. We are in position to speak about cost yet. And this is something that does not is not only for HCMR to answer. iBus is a platform that, as we have just discussed, is a common platform. So there are more partners that are participating, and if we are successful, I'm sure that this is something that we are going to come up, and this is not going to be the problem.
To be solved.
Yeah.
Great. Thanks again, Nikos and Dimitra.
Thank you.
Wonderful. I'd like to invite my colleagues Noel from Norse and Krista from Ovum, one of our collaborating companies. Welcome. Yeah, just we'll get. I can introduce you a little bit, Krista. Tell me a little bit about your background and what you're working on and your contribution to iFishIENCi.
Yeah. First of all, it's very nice to be here, and so much good things have been mentioned already. I'm excited to see the results that will come from this work. I'm here working on Ovum, and we have developed the closed cage system that we call egge, or the egg, thus the name Ovum, for those who understand Latin. Yeah, and I've been working to try to get one of these demo tests in the egg so that we can test it out in the technology, different type of technology, and also the open cage with the fish that has been previously in egg. Yeah.
We're going to show that in a second. And Noel, introduce yourself and your background and your role in iFishIENCi.
Yes, so my name is Noel Garbi. I'm Research Director of the Fish Biology and Aquaculture Group in North, in the Environment and Climate Department. Yes, my role in iFishIENCi is the demonstration, so in Norway. And luckily we have Ovum and Krista with us to discuss it today.
So Frank showed us the infrastructure, and Dimitra and Nico showed us the Greek demo. And so now we're talking about the demo in Norway. And basically, walk us through a little bit, Noel, about the setup here.
Yes, I mean, yeah, it's pretty similar to what Nikos and Frank earlier have been discussing, so all goes together. The idea here, and this video shows in HCMR pilots, and showing also how the sensors and how the cameras are situated in the open cages. So basically we're feeding the fish. We have camera sensors in the cage and looking towards the surface. The idea here is to send the data to the iBoss. So data means streaming, data from like fish behavior or environmental sensors will be there, so you will get an idea about water quality in relation to temperatures or oxygen level as well. So this is really important, and it goes directly to the iBoss cloud and then through machine learning, artificial intelligence. But also I have to point out also the expertise also within the aquaculture sector, meaning fish biology and the technologies as well, rearing technologies. It's very important to link this aspect, and then this goes into this fish talk to me, which we can call it also like the digital fish, that will give us an idea about the status of the fish, if the fish is hungry, the fish is stressed, etc. This is the nice paper that was accepted like 10 days ago, was mentioned by Nikos. So if you want to know more, then just read this paper, and gives you a good example of how the technology has been used here.
So great to get those peer-reviewed papers out that really underscore that this is based on science and a lot of quantification here.
Yes. So we're basically a next step, meaning in any business, on any proposition you make, you have like this roadmap, and one of these roadmap is the experimentation, right? And then how this idea works, and you need to assess, of course, and you go through pilots, you need to trials and so on, and then at some point you move on, and then next step is large scale and full production, and luckily in this roadmap as well, it's really important to have partnership, and we're lucky to have Ovum with us, Oxyguard, HCMR, and EGM, basically to put in place this in a larger scale. And this is our plan. This will be demonstrated both in open cage and semi-closed containment systems. The idea here is to show that we are able to have a real-time streaming and a storage of data in using iBoss system. And then, of course, using the algorithms that were actually described by Nikos earlier and Dimitra, and show that these algorithms are also applicable in different species, but also different technologies. So this is the idea.
Cool. So as I understand, there's two types of structures that we're talking about in this demo. One open cage, and then one the semi-closed containment system. Can you tell me a little bit about how Ovum is working with this demo here?
We want to see how it works in both, just to learn. As we are the company has been working with the system for 10 years already, but this is the first pilot, so there's a lot to learn, not only with this new technology, but also our technology. So we're very eager to learn as fast as possible, as much as possible. So yeah, we'll be placing a camera and connected it to the network to learn from the open cage just next to the egg. And also using the existing infrastructure in the egg to do the same and to see how this works and to see the results and yeah, what can we learn from it first and foremost. Yeah, several people have mentioned it already, that it's this knowledge that needs to be integrated from the people working, like the operators, and if we want to grow and export the technology, we can't send the operators with the technology out in all the cases, at least. So that's what makes it important to get that knowledge connected to the technology so that it can follow the product, because we have seen exceptionally good results in the pilot, but we also have very great people working on the product and with the fish. So this has to follow and be bound up so that it can be exported together.
I wasn't explicit, but of course when we talk about fish, we're talking about Atlantic salmon. Yeah. So this is another species that's training a bit of the behavioral algorithms on. Do we have a lot of data on that already, or do we need to do these more pilot studies to learn how salmon are behaving?
There is some data actually out, and then what's actually based on that, we'll be doing the demonstration and looking at the algorithms also out of it. Of course, the behavior is different from a fish to another, and there will be some differences, of course, but we can also, we're not reinventing the wheel, so we just, use what has been shown, and then we adjust to the species.
So this looks like almost from another planet, the ovum. And when I look at it, the first thing I think about is circularity. This is designed to be a circular system. Inma was talking before today about how to quantify circularity in aquaculture systems. Krista, can you tell me a little bit about the ambitions that Ovum has for circular aquaculture?
Yeah, we definitely want to fit in the circular economy as like a little missing piece. Because if we look at aquaculture today, so there's a lot of outflow of nutrients out in the oceans that we can't get a hold of again. So we have the opportunity to gather this material and bring it back in the economy and shape new products and use them to create value.
And tomorrow we have a workshop on this waste to value product and concept that we've been developing in iFishIENCi, and continuing that collaboration with Ovum on that important topic. I have a question in the chat, and also if there's any questions in the room, we can feel free. A question is there any data on the % cost of feed that we can save relative to growth? Do we have any maybe indication about maybe a hypothesis of how much we can actually save with this technology?
I don't have like a number, but we can definitely save, because we know that the trend is continuous feeding, of course, right? By using the system, and you can actually target when the fish is ready to be fed, right? So you're actually ticking a lot of boxes of this, the environment, of course, because you're minimizing the waste, you're minimizing like feed, but also waste in general. So then you're in a way maximizing profitability. It comes automatically, but also the social aspect and last but not least, the welfare of the fish, right? Because like feeding continuously. So. And just something to remember is like up to 70% actually is of the cost is related to feed in the industry. So it's really, really important. If we feed, instead of feeding continuously and feeding twice like Nikos or like in some other partners do, then you definitely reduce the costs if it's not like half. So it's a lot. And in addition to that, you'll talk about it tomorrow, is the sustainability also of the feed. So that has been tested in iFishIENCi.
Yeah, iFishIENCi has actually been a very ambitious project, hitting a lot of these critical bottlenecks for sustainability for aquaculture. A final reflection, how has it been to work together? Here we have Norse, a research institution, and Ovum as a business. All these good intentions, but of course we're in different sectors. Can you maybe reflect on the possibilities, opportunities, but also the challenges?
You want to start? I start. Well, I mean, it is challenging, of course, right? Like you said, it's different industries, and we do more research, R&Ds and so on. So it's one thing when you do a trial in your own facility in a wet lab, or in the pilot scale, and it's another thing when you go large scale and full production, because that also, I mean, we need to understand that is business as well, and we need to make sure that when we apply this new technologies or any value proposition, it has to work straight forward. And we need to consider the needs as well of the industry. The needs are different, and especially, at least my knowledge is in the Norwegian industry, and there are different needs, right? They adapt a lot to technology. There's a lot that is going on in the Norwegian aquaculture sector, and then you need to really find what is the need. So it's almost like,
Iterative dialogue.
Exactly. It's a lot of dialogue, and I mean, I have really good experience so far with Krista. We had really good dialogue, but of course there are challenges that are out of our hands. So that we need to adapt and adjust.
We don't have these big research test centers full scale, so we're really dependent on that industry collaboration. Your final reflections, Krista, what is Ovum gaining from this collaboration?
Well, we're learning a lot. I think that's, and it is for Ovum one of the priorities to learn quickly. Just as long as we can learn quickly, we can go forward and avoid a lot of the issues maybe others are having. And I think the challenge maybe for the industry is that we have a very narrow focus that we have to stick to, just to be able to move forward and reach the goals. So then the research and development has to kind of fit into this narrow road, just because of limited resources, both time and capacity, finances. So it has to be a good match, because if it draws the focus away, we can stand in the danger of kind of not moving forward in the fronts where we need to in order to stay.
Cool. Mm-hmm. Thank you very much for your reflections, and good luck to the rest of the Norwegian demo. So finally, before our little coffee break, we have a story from Hungary. So I'd like to bring to the stage my colleagues from Hungary, Tomas from Aquabiotech in Malta, project coordinator, but also Hungarian, and Balázs Kovács from Mate, the University of Agriculture and Life Sciences in Hungary. So you guys have been working with African catfish. Tomas, can you give me a little bit about background about catfish farming in Hungary? How big is it? How did it start? What are their ambitions?
I would start with, in general, about the African catfish, and maybe in general about the aquaculture in developing countries as well, because we are end users of this project result a little bit as Aquabiotech, because Aquabiotech is involved in many development projects in Africa and Asia. And what we see, and this is also reflecting to the question what Nikos just received before, that in developing countries, aquaculture 4.0 not necessarily means the digital technologies, but aquaculture 4.0 also include the genetic work, the new genetic methods, new genetic technologies, and this have a greater importance, I think, in the developing countries. So we consider the African catfish work in the project as a potential method and use and product what we can use in our consultancy activities in developing countries. But African catfish, as you mentioned, also important in Europe. Hungary is one of the largest producer country, and I have another hat on me now because I am a big fan of the African catfish as a consumer. I like to eat. I like to eat the products. The story started in Hungary at the end of the 80s when the economic and political change came in the country, and some scientists, some aquaculture researchers realized the potential in this species, and they became a businessman and they started to produce the catfish in Hungary, where we have a resource. We have lots of geothermal water in the country, which is used mainly for heating and in greenhouses and geothermal energy and the water. And the secondary use of this water can be the African catfish production. So the production started and is growing and growing year by year.
So here's a picture of an African catfish, and then they're raised in ponds.
They produce the fish in Hungary in tanks, in large tanks, because and they can achieve a very high density because the fish can breathe air after a certain period, and yeah, it's popular in the market because we had the European catfish on the market before, so the consumers knew the type of the fish a little bit, and the most frequent, most common form on the market is a fresh fillet in the supermarkets.
So you have been working also with stakeholders, with fish farmers in Hungary. Balázs, can you explain a little bit about how you, as a scientist and coming from university in Hungary, have been collaborating and having a dialogue with these fish farmers?
So the main ideas coming from the university okay, so the ideas coming from the university to develop the genetic background of the African catfish in Hungary, because previously, according to our knowledge, there wasn't any selection program in this species. So, and the aim was to selecting the fish for a low fish meal containing feed, to better utilization of this feed in the to develop a line which can be used for that. And African catfish is a very good target for this pilot selection program because it has a very short generation time. So
how long is the generation time?
It's only 8-9 months.
8-9 months, okay.
So it's very good. So in this project we could making a selection through 3-4 generations. So the final generation that we tested was the fourth generation.
Okay.
And the results are very good because in flow through system we could reach 26% gain in this with this line. And we also tested this line in rush systems because of the circularity, and we try to use in other system too. And in this case, this line was more successful because the difference was 30%, and in this case we could detect the difference between the feeds. This line could utilize much better the lower fish meal feeds than the normal control line.
So basically, you're seeing that in developing African catfish for larger production, you're getting good success already with the genetic lines, and that the new feed using, there was a microalgae in this feed.
Yeah, we tested 4 different feeds, and this fish utilized better all the 4, but among that was one which contained the algae from the iFishIENCi project. So it also was a product of the iFishIENCi project. And
I think that microalgae came from here in Bergen, from our Norse colleagues.
Yes, this was produced by the Norse colleagues. And this feed was much better than the control feed. The only difference was between the two feed was the 5% of algae, which the difference in the growth was around 5% again.
Yeah. So really great results, and showing that also the collaboration with the fish farmers. You said something that, here's a picture of you presenting some results. You said that they were actually surprised with the iFishIENCi results. How were they surprised?
Yes, that was a workshop for the African catfish producers, and these producers just realized that how efficient can be the selection in this species, in case of this species, because they thought the genetic background of this fish is weak, but it's not. So it's possible to select this fish.
So they like those results and saw the opportunities.
They want to use this new line for their own production.
So I understand that the production was about 5,000 tons of African catfish, but now it has increased the past years, Thomas?
It's reached 5,000 tons. This year it will be more than 1,000 tons, and it's increasing in Hungary. It has but not just in Hungary. What we saw in Africa as well. We work a lot in the countries around the Lake Victoria, and there around the lake, the most important species is a tilapia, as another species what we work with in the project. But the areas farther from the lake, African catfish is an important species for the aquaculture development in these countries. So we expect that the production will increase in Africa as well.
Great. It's very cool to hear about also this type of technology, looking at sustainable feed, looking at genetic lines in countries where aquaculture is just really starting to develop bigger along the lines of EU policy for a Green Deal and more food security in this. We will now take a coffee break, about 10 minutes. At 11:30, we start our policy roundtable, where we also put this technology and these results into the larger policy frame. So thank you very much.